Hi, and welcome to this next installment in my algebra and pre-calculus video series. In this video, we're going to continue on with our discussions on trigonometric functions. And the focus of this video is going to be doing something we've done previously, evaluating functions. But we're going to be looking at some new functions, not the sine, the cosine, tangent, cosecant, secant, and cotangent. We're going to be looking at the inverses of these functions. And just so you know what's ahead in this video, the problems you see on the screen right now, these are the problems I'm going to be working through later on in the video. And the first thing you notice is, well, there's a couple of, didn't mean to go forward yet. There are a couple of evaluate the trig function. So A and B, evaluate a sine function, evaluate a tangent function in B. And then starting with part C, we've got this -1, right? And what does that -1 mean? That means the inverse function, right? So we have not yet talked about the inverse of the sine, the inverse of the cosine, the inverse of the tangent. I'm going to be sticking with the big three in this video: sine, cosine, tangent. We're not going to talk about cosecant, secant, or cotangent in this video. We're just going to focus on the sine, cosine, and tangents. Okay, so before we get to any of these problems, we have to discuss a little bit in terms of what is the inverse of each trigonometric function. Okay, so we'll start off with a little bit of a review. Find the exact value of the sine of 3 pi over 4. So I'm going to be using the unit circle for the entirety of this video. I'm not going to be using triangles. Right, so to find the exact value of the sine of 3 pi over 4, we go to the unit circle. And on the unit circle, we find the angle of 3 pi over 4, right? And that puts us here at this terminal point. And the sine of an angle, so in this case, the angle is 3 pi over 4. The sine of the angle is the y coordinate, or the y value in the terminal point. So the sine of 3 pi over 4 is equal to positive root 2 over 2, the y value of the terminal point associated with the angle. All right, so this was a topic of a previous video evaluating the 6 trigonometric functions. One more, find the exact value of the tangent of 7 pi over 6. So again, to do this, we go to our unit circle. We look for the angle 7 pi over 6, so that puts us down here at this terminal point. And the tangent of an angle, so again, in this case, the angle is 7 pi over 6. The tangent of an angle is equal to the y coordinate divided by the x coordinate, y over x. Right, so the tangent, let's see what we got here. The tangent of 7 pi over 6 is equal to -1/2, that's the y value, divided by negative square root of 3 over 2, that's the x value. All right, so let's see, we got to simplify this sum. The negative signs cancel, negative over negative, 2 negatives make a positive. And so we could say that's +1/2 times the reciprocal, so keep, change, flip, 2 divided by the square root of 3. Those 2's cancel. We have a 2 on top, 2 on the bottom. So that is 1 over the square root of 3. So the tangent of 7 pi over 6 is 1 over the square root of 3, but this is not considered simplest form or reduced form. We don't want to leave a square root in the denominator, so we're going to go ahead and rationalize this guy. So we'll multiply top and bottom by the square root of 3. Now what that does is it gives us the square root of 9 on the bottom. And the square root of 9 is 3. And then on top, 1 times the square root of 3 is the square root of 3. Okay, so the tangent of 7 pi over 6 is the square root of 3 over 3. Okay, so this is, again, just a little bit of a review evaluating trig functions. You're given an angle. You find the terminal point on the unit circle associated with that angle. That's this guy right here. And then we use the definition. If it's the sine, it's the y value. If it's the cosine, it's the x value. If it's the tangent, it's the y over the x. And the other 3 trig functions are defined in terms of those coordinates as well. So now let's talk about the inverse trigonometric functions. Now, if you're wondering what that blue box is right there, well, that's going to be just a visual aid. Let's say we have some function, some trig function. So I'm using f of theta just to emphasize that our input is an angle. All right, so what goes into this function is the angle theta. And what comes out is something to do with the terminal point. Again, I'm sticking with the unit circle definition. So output is something that has to do with the terminal point on the unit circle. If it's the sine function, then the output is the y value of the terminal point. If it's the cosine function, then the output is the x value of the terminal point, and so on. So let me just pop this back on here. So for a trig function, we input an angle and we output something. Something referring to something about the terminal point. Let's just keep it informal. Something about the terminal point. So, for example, if this was the sine function, then the output would be the y value of the terminal point. Right? If this was the cosine function, then the output would be the x value of the terminal point. We have all these definitions, right? I don't want to spend too much time with them. If this was the tangent function, then the output would be y divided by x. If it was secant, it would be 1 over x. And so we have these 6 trig definitions based on points on the unit circle. So the output is going to be something about the terminal point. Well, if we're going to talk about the inverse, trig functions, well, then the input could be something about the terminal point, and the output should be the angle. Remember, the inverse function reverses or undoes what the original function does. So if the function maps a angle to a value related to the terminal point, well, then the inverse function should take as an input a value related to the terminal point, and the output should be the original angle. Okay, so that's just based on our knowledge of inverse functions. And we covered inverse functions in a video way back in this playlist. I don't know how many videos back it was, but we talked about inverse functions in one of those videos. But the problem is, to talk about a function and its inverse, well, only functions that are one-to-one have an inverse. Only functions that are one-to-one have an inverse. right? So one-to-one functions means no repeated y values. Every x value, every unique x value has a unique y value. Okay, well, this is obviously is going to cause some problems with these trig functions, right? Functions that are not one-to-one do not have inverses. Here's the sine function. Y equals the sine of x, or f of x equals the sine of x, is not one-to-one. So it does not have an inverse. Right? We have this horizontal line test to determine if a function is one-to-one. If a horizontal line hits the graph more than once, the function does not have an inverse, right? So this horizontal line, this blue line I just drew, hits the graph in many places, infinitely many places, actually. So we cannot talk about the inverse of the sine function. Doesn't work. But let me get rid of this blue here. What we can do is look at just a part of the graph, just a piece of it. So that blue highlighted portion of the graph, well, that is one-to-one. Right? No horizontal line is going to touch that blue portion more than once. So if we're going to talk about the inverse of the sine function, we can't look at the whole graph. We can't look at the whole domain. We have to restrict the domain and look at only a piece of the graph. So if we look at the graph of sine of x only for x values from negative pi over 2 to pi over 2, then this function is one-to-one. Let me go back to the previous slide. Not one-to-one, the red one is one-to-one, the blue one. Not one-to-one is one-to-one. So as soon as we do this, as soon as we restrict the domain, then, only then, are we able to talk about the inverse of the sine function. Now, if we look at the x-axis, this is negative pi over 2 to pi over 2. Now remember, the x-axis, these are angles. So we're only looking at angles from negative pi over 2 to positive pi over 2. So that's not the whole unit circle. We can't look at the whole unit circle. That is actually the right half of the unit circle. So an angle of negative pi over 2 puts you down here. An angle of positive pi over 2 puts you up here. So previously, if we look at the entire unit circle, then these three angles down here, this one, and this one, would be positive numbers. Five pi over 3, 7 pi over 4, 11 pi over 6, right? But we're not going to look at those positive angles, because to get those positive angles, we have to wrap around the other side of the unit circle, but that other side doesn't exist right now, right? So we have to look at now negative angles. So this would be an angle of negative pi over 6. We talked about coterminal angles, I think, in the very first trig video in this series. We talked about coterminal angles. So negative pi over 6 and 11 pi over 6 give you the same terminal point. Right? This one will be negative pi over 4. And this guy would be negative pi over 3. So if we're going to, again, if we're going to talk about inverse trig functions, this is the portion of the domain that we are allowed to consider for x values that are between negative pi over 2 and positive pi over 2. And if we do that, then this piece of the graph, this portion of the function, is 1-to-1. Okay, so that's the sine function. What about the cosine function? This is the graph of y equals the cosine of x. Well, again, not 1-to-1. Horizontal line, again, obviously hits the graph more than one place. But what if we do the exact same thing as we did with the sine function? Only look from negative pi over 2 to pi over 2. Well, that doesn't work because this, even this little blue portion, doesn't pass the horizontal line test. So we can't do the same thing with the cosine function as we did with the sine function. So we're not going to do negative pi over 2 to pi over 2, which was the right half of the unit circle. But we could look at a different interval. What about this one that I just highlighted green? Right? That looks like a piece of the graph that will pass the horizontal line test. That will be 1-to-1. So if we restrict the domain, we use the interval 0 to pi, then that portion of the cosine graph is 1-to-1. So let's erase the rest, get rid of the red, and just leave the blue part. So now we have the graph of y equals the cosine of x, only this little window from 0 to pi. And if you think about the unit circle, 0 to pi is going to be the top half, the top semicircle. This is an angle of pi. Pi is half the circle. So to talk about the inverse cosine function, the inverse of y equals the cosine of x, then we could only consider this interval in the domain 0 to pi. All right, and we should probably talk about the tangent function as well. Right, this is the graph of the tangent of x. Again, doesn't pass the horizontal line test. Right, the horizontal line hits the graph in many places. Right, so that is not 1-to-1. But again, we'll do the same thing with the tangent as we did with the sine and the cosine. We'll restrict the domain. And if we look at just one copy of the tangent graph, so on the x-axis, negative pi over 2 to pi over 2. Actually, we have to be a little bit more specific here. I'm actually going to rewrite this as negative pi over 2 to pi over 2, but not including the endpoints, because remember, the tangent of pi over 2 is undefined, and the tangent of negative pi over 2 is undefined. That's where the vertical asymptotes are. But we do the same thing. We restrict the domain, and now we have a portion or a piece of the tangent graph that is 1-to-1. So when it comes down to evaluating inverse trig functions, we just have to make sure we're using the right part, right? We're only taking part of the graph, and we're only going to use part of the unit circle. For the tangent, it's the right half or the right semicircle. For the sine, it's the right half. And for the cosine, it's the top half. So I think now we're ready to evaluate some inverse trigonometric functions. So for the inverse of the sine function and the inverse of the tangent function, we're looking at only the right half of the unit circle. So this would be negative pi over 6. This would be negative pi over 4. This would be negative pi over 3. And then for the cosine function and the inverse of the cosine function, we're looking only at the top half from 0 to pi. We don't have to worry about negative angles for the cosine function because that's 0 to pi. Everything above 0 up until pi is a positive angle. Okay, so let's see if we can put this into action, evaluate some inverse trig functions. So first problem, evaluate or find the exact value of the sine inverse of 1/2. Well, remember what the sine function does, right? It's a function. The input is an angle. So let's say f of theta is equal to the sine of theta. We could use x or theta, doesn't matter. Since I'm thinking in terms of the circle, I'm going to use theta. And the output is the y value of the terminal point, right? The y value of the terminal point. So what does the inverse function do? So it's sine inverse of theta. What does it do? Well, it takes the y value as the input, and it spits out an angle. So the question is, what angle has a terminal point with a y value? We're talking about sine, so it's the y value. What angle has a terminal point with a y value of 1/2? Right? That's what this is saying. Right? Because the sine inverse of a half is going to equal some angle. We have to figure out, like, what is this angle? What is this angle? The y value has to be a half. Because it's the sine inverse, what we have to do is go to the right half of the unit circle. Right? It's sine inverse, so we talk about the right half of the circle. We look for a point that has a y value of 1/2. And that point is associated with this angle. So the sine inverse of 1/2 is equal to pi over 6, right? We're basically given the y value. We want to find the angle, right? There's nothing to calculate here. There's not like a step-by-step algorithmic approach other than look at the right side of the unit circle, find the number 1/2 as it appears as a y value, and the answer is the associated angle, pi over 6. All right, so let's do some more of these. Let's do some more. This was just number 1. Well, 1C, our first inverse trig function. Find the exact value of sine inverse of √3/2. Okay, step 1, it is sine inverse. So that tells us go here. It's sine inverse, so go to the right side of the unit circle. Look for the number √3/2, positive √3/2. And the angle that gives you that terminal point is associated with an angle of pi over 3. So the answer is pi over 3. And that's about it. That's about it. Just we want to make sure we're using the correct part of the unit circle. Remember, to talk about inverse trig functions, we had to restrict the domain. Only look at a portion of the function. So that means we're only looking at a portion of the unit circle. Find the exact value of the cosine of √2/2. Sorry, not cosine. The cosine inverse of √2/2. Well, it's cosine inverse, so we go to the top half of the unit circle, right? This is telling us to use this, top half. Cosine inverse, top half. Sine inverse, right half. Tangent inverse, right half. Right? So we're using the top half of the unit circle. We're looking for a positive square root of 2/2 for the x value. Remember, cosine goes with x, sine goes with y. So we're talking about cosine inverse. So x equals √2/2, theta equals question mark. That's what we're doing. Right? So there's an x value of positive √2/2. So our angle is pi over 4. All right, evaluating trig functions. You start with the angle, you find the terminal point. Evaluating inverse trig functions. You start with the terminal point and you find the angle. All right, let's keep going. Find the exact value of the cosine inverse of -1. So again, it's cosine inverse, so we go here, top half of the unit circle. We're looking for -1 as an x value. Remember, x equals -1, angle equals question mark. And there's our angle right here. Angle is pi. So the cosine inverse of -1 is pi. All right, looks good. Looks good. So sine inverse and cosine inverse, these two are a little bit more straightforward than the tangent, right? Because the sine is the y value. You read it directly off this unit circle. The cosine is the x value. You read it directly off this unit circle. But what about the tangent? Find the exact value of the tangent of negative root 3. Well, step one, because it's the tangent inverse, we go to the right half of the unit circle, right? Tangent inverse tells us to use the right half. So now we have to find the point where the tangent is negative square root of 3. Right, so tangent is y over x. So the y over x is negative square root of 3. Angle is our question mark. So which angle gives us a tangent of negative square root of 3? It might be in your best interest if you have a printed out version of the unit circle next to each terminal point. Write the tangent value. So the tangent of pi over 3 is the square root of 3. The tangent of pi over 2 is equal to 1. And the tangent of pi over 6, oh, sorry, not pi over 2, that's pi over 4. Apologies. And the tangent of pi over 6 is equal to root 3 over 3. This one we did earlier in this video, tangent of pi over 6. And since the fourth quadrant is a reflection of the first quadrant, and this angle, why does that keep coming back? This angle is negative pi over 6. This angle is negative pi over 4. This angle is negative pi over 3. So the tangent of negative pi over 6 is going to be negative square root of 3 over 3. The tangent of negative pi over 4 is negative 1. So we're getting the same value. Not oh yeah, negative root 3 over 3. That's right. Sorry, I'm trying to squeeze it in here at the very edge of the screen. And the tangent of negative pi over 3 is a reflection of tangent of pi over 3. So that's going to be negative square root of 3. Now, it's helpful to write these values. Again, if you have a unit circle that's written out or printed out, the points, that's the sine and the cosine, right? The cosine is x, the sine is y. So maybe off to the side, give the tangent value, y over x. Negative root 3 would be the tangent of negative pi over 3. Right, so here's our angle. This terminal point gives us the value of negative square root of 3. So the tangent inverse, remember, we're looking for the angle. The tangent inverse of negative square root of 3 is equal to negative pi over 3. That's our answer. So these 6 values that I have written here in red, I'm not going to be rewriting them on every slide moving forward every time we have a tangent function. But square root of 3, 1, and root 3 over 3. And then we've got negative square root of 3, negative 1, and negative root 3 over 3. These are the 6 tangent values for those 6 angles that are labeled on the unit circle. Good to have those ready to go. Okay, what is the exact value of the tangent inverse of root 3 over 3? Well, it's tangent inverse. So that tells us we go to the right side of the unit circle. The tangent of pi over 6 is equal to, that's a 2, root 3 over 3. So the tangent inverse of root 3 over 3 is equal to the angle pi over 6. Pi over 6. All right. Tangent is root 3. Tangent is 1. Tangent is root 3 over 3. Tangent is negative root 3 over 3. Tangent is negative 1. And tangent is negative root 3. All right. So we just have to find the angle that gives us this tangent value. All right. So now the next step is to talk about the relationship between a function and its inverse. So what we saw previously, before we started talking about trig functions, before we started trigonometry, we talked about functions and the inverse functions. A function and its inverse. What we saw was that if two functions are inverses of each other, then if you compose them, f inverse of x, you get x, and f inverse of f of x, you also get x. So essentially what happens is the function and its inverse cancel, and you're left with just x. And that's actually what happens here. The sine inverse and the sine cancel, and the answer is pi over 4. Right? But I don't think it's a good idea to look at the problem this way, because these two functions have different domains. Right? If we just look at the sine function, the sine of pi, well, not of sine of pi over 4, the sine function, well, the domain is negative infinity to infinity. But if we talk about the sine inverse function, the domain is not negative infinity to infinity. The domain is, let me use brackets, negative pi over 2 to pi over 2. So they have different domains, right? Not every number that works for the sine function also works for the sine inverse function. Right? So let's not think about inverse functions this way when we're talking about trig functions, because the domains don't line up. So I think a better way to approach this problem Let's use two steps. What is the sine inverse of the sine of, well, I don't need extra parentheses, but yeah, let's just say the sine inverse of the sine of pi over 4. Well, we could do this, right? Ignore the outside. Ignore the sine inverse portion just for now. It's, it's a two-step process. Let's do the sine, and then we'll do the sine inverse. All right, we'll start with the sine of pi over 4. We'll do this in 2 steps. Work inside parentheses and then outside. So this is equal to the sine inverse of the sine of pi over 4. And the sine of pi over 4 is the square root of 2 over 2. So now we need the sine inverse of the square root of 2 over 2. And because we have the sine inverse, that tells us we got to go to the right half of the unit circle. So let me rewrite what we had on that previous slide. Sine inverse of sine of pi over 4. Oh, again, too many parentheses. Don't need them. Is equal to the sine inverse of root 2 over 2. So now we find square root of 2 over 2 as a y value. And the angle is pi over 4. Well, I know what you're thinking, Eric. Why? Why couldn't we just cancel the inverse and the function and say the answer is pi over 4? Because it works, only sometimes. It works for this problem, right? The sine inverse of the sine of pi over 4, the sine inverse and the sine cancel because there's no issue with the domain. But that's not always the case. That's not always the case. So I think step 1, do the inside. Step 2, do the outside, inside function, then outside function. I think this is a better approach because this works all the time. This works all the time, where canceling only works sometimes. Okay, what is the exact value of the cosine inverse of the cosine of 4 pi over 5? Well, in this problem, this is not an angle we're familiar with, right? If it was cosine of 5 pi over 4, okay, we're good with that. But 4 pi over 5, that's not an angle that has a terminal point that we're familiar with. But the cosine inverse function has a domain from 0 to pi. Right? This angle, 4 pi over 5, is inside that interval. It's between 0 and pi. So there's no issues with the domain. So we could cancel, and we get 4 pi over 5. Four pi over 5 will be somewhere over here. Right? And that's in the top half of the unit circle. But now let's look at a problem here. Well, the sine inverse of the sine of 5 pi over 4. I'll tell you right now, we can't cancel, and say this is equal to 5 pi over 4. Right? This one does not work. We're talking about the sine inverse. Right? So because we're talking about the sine inverse, we go to the right side of the unit circle. 5 pi over 4, if we look at this angle here, 5 pi over 4 is over here somewhere. It's on the other half. The other half doesn't exist right now, right? We're only able to look at the right side of the unit circle. But it's not a problem. It's not a problem. We just do this in 2 steps. The sine inverse of the sine of 5 pi over 4. Right. The sine function, we use the whole unit circle. We don't need to look at just the half. That's the half is only for the inverse function. The half is only for the inverse function. For the sine of pi over 4, we go to the unit circle. See if I have that. No, I don't. The sine of 5 pi over 4 is equal to, that's going to be negative square root of 2 over 2. We get that from the unit circle. Hopefully at this point, evaluating trig functions is something you're able to do. If not, definitely want to go back and review that. All right, so the sine of 5 pi over 4 is negative root 2 over 2. And now we can look at the sine inverse. Right, remember step 1, inside function, step 2, outside function, right? So we did step 1, now we're on to step 2, the sine inverse part. Sine inverse of negative root 2 over 2. We got to find a point where the y value is negative root 2 over 2. Right? There's a y value of negative root 2 over 2. And that's going to be an angle of negative pi over 4. So the sine inverse of the sine of 5 pi over 4 is equal to, not 5 pi over 4, but negative pi over 4. And again, if you think back in previously in this video, earlier in this video, we started off by part A and B, evaluate trig functions, and then C, D, E, F, G, H, I, J, and K, evaluate inverse functions. So this is just 2 problems in one. Step 1, evaluate a trig function, and then step 2, evaluate an inverse trig functions. All right, just 2 things, 2 steps. All right, let's do one more. Find the exact value of the tangent inverse of the tangent of 3 pi over 4. Well, because we have the tangent inverse function, we know we need to go to the right side of the unit circle. 3 pi over 4 is over here, right? It's in the wrong quadrant. It's in quadrant 2. So this would be an angle of 3 pi over 4. Can't do that, right? There is no 3 pi over 4 for this guy. There is no 3 pi over 4 for the tangent inverse function. So we start with this. What is the tangent of 3 pi over 4? Well, that's going to be negative 1. Right? When your angle is 3 pi over 4, your terminal point is negative root 2 over 2, comma, positive root 2 over 2. Tangent of theta is y over x. So that's root 2 over 2 divided by negative root 2 over 2. Any number divided by itself is equal to 1. We got a negative sign, so that's negative 1. So the tangent inverse of the tangent of 3 pi over 4 is equal to the tangent inverse of negative 1. Now, what is the tangent inverse of negative 1? Well, we need to find a terminal point that gives us a negative 1 when we do y divided by x, and that's going to be this guy down here. The tangent of theta is negative 1 when our angle is negative pi over 4. Negative pi over 4. Again, it's helpful, I think, to write the tangent values next to each point. So then you've got the sine, the cosine, and the tangent. This is cosine, this is sine, this is tangent. All right, so you got all three. But again, if you have a unit circle, write those 6 numbers down. So it's just it's easier to locate the terminal points. So the tangent inverse of the tangent of 3 pi over 4 is going to be negative pi over 4. That's our final answer. All right, looking good. Looking good so far. So let's move on. Only a couple more to do. Use a calculator to find the value of the following expression. So no longer we're looking for exact values. The only time we're using the unit circle or half of the unit circle is when we're looking for exact values. But we could only find exact values at this point when our angles are some multiple of 30 degrees or some multiple of pi over 6 or some multiple of 45 degrees or pi over 4. So if our angle is not a multiple of one of those numbers, we got to use the calculator. All right, so we're going to round to 2 decimal places. So let's look at this first one. The cosine inverse of the square root of 3 over 6. Well, the directions say, give your answer in radians, rounded to 2 decimal places. Give your answer in radians. So what's the first thing we have to do here if we're using a calculator? Well, if we open up our calculator, we want to make sure we go into mode. And because angles, we can measure in degrees, and we could also measure in radians. This problem is talking about radians, so we want to make sure our calculator is in radian mode, right? My calculator is not. It's in degree mode right now. So you see that third row down, you see radian and degree. My calculator is in degree mode. So if I typed in the cosine inverse of square root of 3 over 6, I would get the wrong answer. So first thing we got to do Move the blinking cursor down to radian, hit enter. So now I am in radian mode. So I'll do second mode to quit out of there. Now you'll see on the keypad, there's a sine button, a cosine button, and a tangent button. And directly above those buttons written in blue, you'll see sine -1, cosine -1, and tangent -1. The -1 is the notation for inverse. So if we want the cosine inverse, we got to hit second cosine. All right, second cosine. So now you see on my screen, on my calculator screen, cosine -1, which means cosine inverse. There's another word for this, or another name for this, called the arc cosine. We're not going to talk about that now. We're just going to use the standard algebra notation for inverse, which is a -1. But if you come across the term arc cosine, ARC-COS, it means cosine inverse. Okay, so we want the square root of 3. The square root is above the x squared, or above the squared button. So second x squared will give us a square root. Square root of 3. I'll use the right hand arrow to get the cursor out of the square root. Fraction means division, so divided by 6. All right, so there's the cosine inverse of the square root of 3 divided by 6. I already made sure my calculator is in radian mode, so we should be good to go. 1.277953 something something something. We want to round to 2 decimal places, so it looks like 1 point. We're going to go with 28 radians. 1.28. I use the squiggly equal sign because that means approximately equal to. So the cosine inverse of the square root of 3 over 6, it's not equal 1.28, but it's very close. We rounded it to 2 places, 2 decimal places. All right, and then the last one I want to do here, let me move the calculator to the other side, is the tangent inverse of -27. So we'll go second tangent to bring up tangent inverse. -27. Make sure you're using the negative sign down here, not the minus key. If you do -27, you're going to get an error. Right? You're going to get an error. We have to do second tangent, negative sign down here, -27. And so when we round this to 2 decimal places, it looks like we get about -1.53. -1.53. All right, and that does it. So this is all of the problems that were given on the very first slide. Number 1, A through L, I think it was L maybe. Number 2, A and B. I want to just do one more problem because, there's one thing we didn't actually touch on yet in this video, and that was the directions for problem 1. It said find the exact value or state. Let me go back some slides here. I'm going to go all the way back to the beginning. Yeah, I'm going to keep going back. Sorry, bear with me. Find the exact value of each of the trigonometric functions, or state that they are undefined. Or state that they are undefined. Well, what would make a trig function undefined? Or in this case, an inverse trig function? Well, let's just do one example. What is the sine inverse of 3 over 2? What is the sine inverse of 3 over 2? Well, again, this is what we've just did about a dozen of these. When you're evaluating a trig function, you start with an angle. When you're evaluating an inverse trig function, you're starting with something to do with a terminal point. So to evaluate this, it's the question if the y value of the terminal point is 3 over 2, what is the angle theta? Right? What angle gives you a terminal point where the y value is 3 over 2? Well, 3 over 2 is bigger than 1. It's 1.5. There are no points on the unit circle where the y value is 1.5. There are no points on the graph of the sine function where the y value is 1.5. The maximum is 1. The minimum is -1. So there are no points where the y value is 1.5. So the answer would be, I'll write it in green for final answer, would be undefined. And that's because this number in here is too big. It's bigger than 1. So there are no points on the graph of the sine function, or there are no points on the unit circle where the y value is 1.5. Okay, just wanted to throw that in there just so we covered all of our bases. So that's it for evaluating inverse trig functions. In the next video, I think I'm probably going to split that into 2 short videos. We're going to look at a couple applications, a couple word problems. And in those word problems, we're going to have to use some of these inverse trig functions. All right, that's it for now. I hope this was helpful.